Use our first presenter, Mark Hallward. Mark is the Global Pharma and Senior GMP Advisor in the Life Science Division of Particle Measurement System. He has a long career in contamination control, managing the design, installation, and validation of over 200 environmental monitoring system projects worldwide. And he designed several products specific for pharmaceutical environmental monitoring, lecture for PDA, EASP, and other international pharmaceutical societies. Our second presenter is Giulia Artalli, Global Product Line Manager, Microbiology and Sterility, also in the, of course, in the Life Science Division, and she has an extensive professional experience of over 20 years supporting pharmaceutical companies.
Let's start at the start, and by looking at, what is optimal microbial sampling? Why are we looking at the optimization of it? From that, there's some key attributes. There's impaction, there's isokinetic sampling, there's the flow rate of the instrument, and there's false positive identification. So there's a lot of subtle nuances between finding the right balance for what you're looking for. And as always with microbiology, it depends. So there's this huge, well, if it depends, what's the perfect solution? It depends on what you're looking for in what environment. What's your humidity? What's your temperature? Is it grade A? Is it grade D? What needs to be done? And then we'll look at some available resources and instrumentation that we can bring that either biases some of these attributes and lessons on some of the others, or looks more holistically at trying to get a balance of everything to optimize what we do. And then we'll look at closing the session out with a Q&A session. If anybody has questions, like Ilaria said, then we'd be happy to field some questions from you. So, introduction. Microbiological sampling within a pharmaceutical manufacturing facility is performed using several methods. Surface, passive air, that's your settle plates. And what we're going to look at here is that active air environmental monitoring sample. And each of those methods will produce a result based upon the growth. So this is traditional of the species on a either specific media, typically agar, and using very specific instruments and techniques. And how you take those samples really does depend on the location of the sample and the equipment that you're using. Now, Annex 1 is pretty specific when it says that the results from any individual element do not constitute evidence of asepsis. And so all of the elements in sampling should be used collectively in support of sterility assurance, and it's given in the current version. So it says it should be noted that the reliability of each of those elements of a monitoring system, viable, non-viable, and APFs, when taken in isolation, is limited. So this is one where don't focus on one aspect. Let's look at my 5 micron particles, for instance. Let's take this out of microbiology. If I have 5 micron particles, or if I have 0.5 micron particles, I'm going to align some contamination control strategy against limits that are set on those, and even the limits that are defined for my microbial sampling. And it's saying, no, you have to look more holistically at whether or not this is demonstrating a shift from control to out of control. And it could be that your data is spiky, and with microbial monitoring, we've got this statistics of small numbers where even a single growth in a grade A environment requires an investigation. And it's in that investigation, where do you go with it? Well, it could be that somebody opened a door, in which case it can be translatable to a function within the clean room, and therefore does that put product at risk? It's a high likelihood of that. If I get CFU activity and 5 micron activity, then those 5 microns are indicative of free-floating microbial activity in a clean room, and therefore there's a high probability that I've got free-floating microbes within my system. And if that's a laminar flow bench, then great, because I've got operators in close proximity to that, and therefore something else broke down. But if it's an isolator, where are those 5 microns coming from that may have yielded my microbial growth? Now, they're rare occasions, because certainly as we get towards isolators, finding CFU is an art more than routine monitoring. We get a lot of zeros. So how I take that sample has to be optimized for that whole environment. So when we start to look at the various elements within that, there's different efficiency. So we have our collection efficiency for air samplers, and that's the physical and biological, and we can control those relative to a series of functions within there. The impaction of microbes onto the collection media is probably the primary method driving collection, overall collection efficiency, but there are secondary functions that we consider. So impaction, as we said, this is probably, it's that initial collection that's the primary differentiator when you start to look at different techniques and technologies. And certainly if you compare the extremes of that, high velocity impaction using, say, slit to agar versus a settle plate, which is a sedimentation velocity. So here we have 0.45 meters per second, and at the other scale with slit to agar, probably closer to 70 meters per second. So we've got that whole range. We know we can collect at 0, and we know, or 0.45, and we know we can collect at 70. So what's the best? Where's optimum? Somewhere along that axis, along that curve. So the inlet velocity directly correlates to the impaction velocity, which then supports the collection efficiency of the device, including, biological efficiency. If you collect them too quickly, then you might damage cellular activity, the cell walls, and you stress the organism and it doesn't want to grow. That it's Tuesday. And then at 0, at 0.45 meters per second, that collection velocity is sedimentation. And so even delicate flora and fauna that might land on the agar will grow out. But of course, there's this probability that it'll land. Whereas with dynamic monitoring, it's quantitative data. So we have this qualitative, is there growth, isn't there growth? Okay, CFU per unit area per unit time. But now we have CFU per unit volume, which correlates, it's a quantitative function from that environment. Isokinetic sampling is a function where the sampled inlet to the inlet is balanced to match the same flow rate as the airflow. So you have your inlet and 0.45 optimum meters per second flow rate, plus or minus 20% and more nowadays. So it'll result in an undisrupted airflow. So as you have that knife edge, the airflow passes down and is undisrupted. There's no disruption to the airflow. There's no recirculation on the back end. It is a true sample. Now, at the speeds that we're talking about, 0.45 meters per second, when you start to look at isokinetic sampling, it's they're fairly slow relative to a lot of isokinetic sampling in ductwork, for instance, where particles have a high velocity. And the smaller particles are more likely to move with the airflow streamlines, as in they are in impaction, than the larger particles. So the large ones maintain their trajectory regardless of airflow. And we'll look at that when we look at impaction. The flow rate through the collection device, the higher the flow rate, the higher the velocity. So the greater the impaction velocity. And they can range from really low, 1 or 2 liters per minute, up to over 200 liter per minute flow rates. But a lot of the instruments that are available and a lot of the instruments that we see in the field now are 25 to 100 liters per minute. And then false positive identification. This is the ability to determine if the contamination has come as a result of the actual environment or if it's a result of poor handling practices, i.e., when the lid was removed and the plates were exchanged, or when it was being transferred to the incubator, or within the incubator itself, and I get growth in an unusual location on the plate itself, whether there was to be a thumbprint, in the worst case scenario. But is there an ability to go, when I'm doing my investigation, if I've got a positive growth, I have to do an investigation, and can I identify whether that was a true environmental microbe or whether or not it's a potential from secondary handling? Now, if it's a potential from secondary handling, that's even worse, because now I have to investigate how that happened. And it's a lot easier to say, okay, I've got a CFU from the environment, and now I can go and challenge where that came from. So when we look at impaction, we have the microorganism or the particle that will flow according to its trajectory. So in S1, where we have a narrow trajectory, there'll be no impaction, i.e. it's a smaller particle and it's able to follow the air streamline as it comes through the hole or the slit within the impactor. With S2, that's this height between the median flow rate of the air and the top of the media. If S2 is reached, then impaction will occur, and larger particles that have that greater momentum will impact onto the surface of the agar. And that's a function between the bottom of the slit and the top of the agar. And that optimal height is set between 0.5 and 1.5 millimeters between those two, the media and the inlet aperture. So when the impaction trajectory is large relative to nozzle width, it'll just follow through. So one of the instruments that we look at has an adjustable base plate, and each click allows for the elevation or lowering of that media relative to the height of the base of the inlet aperture. So that means we can optimize the impaction velocity regardless of media type, media fill, plate diameter, because 30 mil pore in a 90 mil plate is different to a 30 mil pore in an 87.1 millimeter plate. There's a slight difference in height, and that height can be adjusted and accommodated for, which becomes critical when you're trying to get your D50 of less than 2 microns, ideally closer to 1. So how we look at impaction becomes key. And now when I said that D50 result optimally around less than 2 microns, ISO EN, the European normative 17141, talks about ideal impactors having an efficiency, a D50 of less than 2 microns. So that D50 is the efficiency cutoff relative to velocity. Now, this is May's data, so it's a Moller's interpretation of May's data, and we can see the velocity lines as they intersect the 50% efficiency curve. And at 25 liters per minute, we're looking at just over 2 microns, and 50 or 100 liters per minute has a velocity of 20.83 meters per second impaction velocity. So 20.83 gives us just over 1 micron in size. So that's the velocity at which, regardless of how they get there, if an impaction at 10 meters per second, as we see here, we're going to collect in the order of 2 microns, and they're going to follow the smaller, anything less than 2 micron will follow that trajectory and not be collected. Anything greater, so the 3s, 4, 5s, and 10s, the macro particles, those particles that are traditionally associated with microbial activity, they're going to be collected. So that's not an issue. But that's one way of looking at it, and there's 3. So we could look at fluid dynamics, and that's you follow the impaction formula for fluid dynamics, and that gives us the velocity of impaction relative to air density and the slit width and the Cunningham slip factor. Now that's where the airstream moves in one direction and it drags a particle with it. So it's not pushing, it's really more dragging it with it. and it's that drag slip coefficient. So when we start to look at fluid dynamics, at 25 liters per minute, we're again in that approximately around 2.2 microns. And at 50 to 100, it's 1.3 for impingement velocity, and that's a 2.46 from an empirical formula. Now, as I said earlier, there's the ISO EN. They give their own formula in section E5.2, and this is relative to the, again, it kind of compiles a lot of those different functions from above and makes more of a functional set or a functional number of a lot of the different areas, air viscosity, etc. So at 25 liters per minute, we're at 1.4, but using the D50, the ISO 17141 formula are at 0.6. So it actually biases to a smaller size because it compensates for a lot of different elements. So if we take the D50 from ISO, add it to the 2.2 above, we end up in that 1.4 sort of territory. And the faster we go, the smaller the average D50 becomes. So when we start to look at impaction, again, there's no single way of looking at impaction. So what's optimal? Well, we're talking about somewhere between 0 and 70 meters per second. There's this kind of data. So parameters and testing the design have been performed in accordance with ISO 14698, and that's because we're looking for not only the physical impaction collection efficiency, but also the biological collection efficiency, and that's the ability for microbes to grow, specific microbes that they have in the test script, specific microbes to grow once they've been impacted, because they have to overcome the stresses of impaction. So faster isn't necessarily better because of the type of microbes that you might be looking for, and that will change based upon your site flora and fauna, which is why a lot of growth promotion testing goes, here's your standard 7, but add 3 of your own, because those 3 are also critical in you understanding your site. So we're back to, it depends. Isokinetic sampling, there's an optimum airflow rate within unidirectional airflow, which is defined as 90 feet per minute. That translates to 0.45 meters per second. So if you want to know where the 0.45 plus or minus 20 comes from, it's from the old federal standard, which had the optimum as 90 feet per minute. And a lot of electronic semiconductor companies still talk about 90 feet per minute flow rates, which gives them laminar flow. Now, we don't talk about laminar flow anymore. It's unidirectional. And in fact, we've moved away from unidirectional. It's first air. So it's that air that happens before it hits any other surface that might cause turbulence or disruption to that primary flow. So any disruption to flow it negates first air. So as we can see with a nice sharp razor edge, we've got undisrupted flow. If we have too small an opening, we start to draw in the smaller particles. Now, when I talk about smaller, there's actually some contention at the moment. We're talking about 0.1, the sub-micron particles. And macro particles will just keep on their trajectory regardless. Subisokinetic sampling is where your velocity is either too low or your opening is too large, such that the larger particles are going to maintain their trajectory, and those smaller, the 0.5s, the 0.1s, the 0.2s. I mean, 0.5 is still a large particle relative to impaction. So we're talking about, super fine particles, the ultra fine. If you look at ISO 14644, this is the U descriptor of particles within those environments. So in sampling with an improper velocity into the sample probe, anisokinetic conditions, whether it be super or sub, affect the data from a distribution perspective. They're still going to collect the right volume of air, but it's the smaller particles that might be deflected. So it's that sub 2 micron certainly are more likely to be disrupted from the collection plane. They're going to follow the flow lines. But the macro particles, those that we're most important or most interested in, they're going to be collected regarding flow rate is, because again, they're collected at 0.45. So at 10 meters per second, there's an active sampling, and that's our lowest velocity, 25 liters per minute. There's still active sampling taking place. We're still disrupting this airflow, but it has to draw that sample in, and it will over collect the macro particles relative to the micro particles. So if it's sub 0.5, sub 1 microns, sub 0.01 microns, that's when they're going to start being deflected. But anything 1 microns and up will be oversampled relative to the small particles. So it doesn't take a lesser sample, it just shifts the curve of distribution of particles. And when we look at isokinetic sampling probes, we have the razor edge of a true isokinetic probe. This is what we use for particle counting in first air, in laminar flow. They were designed for 0.45 laminar flow rates. But when we start to look at surfaces for microbial sampling, this is no longer a sharp razor edge. This is now a flat surface. So we're going to have its own series of impaction. We're going to see some deflection as the sample is drawn nearer to that sampling plane. So there will be disruption based upon, so isokinetic sampling isn't viable because we don't have an isokinetic shaped probe. Now we could use this in conjunction with an isokinetic probe that then funnels into this chamber. And we have remote sampling kits for that, where, remote sampling or isokinetic sampling is critical, but now you need sample tubing, and you're going to experience sedimentation losses regardless of any length of tube. Even, a few centimeters of tubing, you're going to see sedimentation within the tube. So again, you could do perfect isokinetic sampling, but lose through sedimentation or transport in tubing. So again, it's a balance. It depends. So this flat surface, it's a flat top. It's designed predominantly to take a 90 millimeter or 100 millimeter plate that fits flat within that chamber. So unless you just had it chamfered, your collector is shaped straight onto your plate, in which case there's now no impaction. It's just a funnel for 0.45 meters per second. We have active air, so you're not going to get that function. Now, microbial samplers are designed to optimize impaction with the accommodation of a plate. So the direction from Annex 1 isn't that isokinetic sampling is critical, it's that it doesn't disrupt the critical airflow. As it's being collected, it doesn't create that excess turbulence that now affects first air. Now, with a lot of microbial samplers, they're at the plane of the process. So it's no longer important that you see disruption because we're below the critical first air points. So we tend to be monitoring below that first air process impaction plane. With particle counting, you want to be above that plane, otherwise you just get process signature and it looks noisy and you have to differentiate that. But with microbial sampling, we're looking for anything that exists anywhere within that environment. And so we tend to be more deck height or more aligned with the tops of the vials. But my particle counting was slightly above that because we're monitoring the quality of first air as it washes over the process. So the placement of the device itself within unidirectional airflow is meant such that it doesn't disrupt the airflow pattern. And that means that with single plates, it's easy because the vacuum is outside. But when you put the whole instrument in, you have to be aware of, if it's 100 liters in, it's 100 liters out. To make sure that that clean air that's coming out is clean, and we're not now, spewing desiccated media all over the surfaces, but also that turbulence that comes out of that small exhaust port doesn't then disrupt and cause turbulence on those critical surfaces where you're now looking for, your surface monitoring. when we think about settle plates, we have static air here. And as the particles tend to come down, because we have a zero stasis point, there's no airflow. What tends to happen is that the particles divert from there. So the smaller particles, again, macro particles, 5, 10 microns and greater, have inertia, they will be collected. But the maths for impaction, which you can't do because there's no impaction plane, the maths for impaction for settle plates is really sketchy. And the smaller particles will always follow the flow streams. So this is another reason why, settle plates or static monitoring, passive monitoring is really difficult to use as a tool for your grade A isolated type environments. Again, no single piece of data. So volume flow rate, there is a relationship between volume flow rate and the desiccation of media. The faster the flow rate, the quicker the media will desiccate out. And so the active sampling, desiccation of localized airflow can be accelerated as a function of the instrument flow rate. So higher the flow rate, faster the desiccation rate. So the rate is over time. So the BioCap single use uses an impact has been demonstrated to collect up to 4 hours. And again, that's a site determined environmental condition, because if it's dry air or low humidity air or warm air, then desiccation will occur at a different rate. So you just need to go through some site validation. I say that quickly and glibly. There's a process in doing that. But traditionally, high flow rate instruments require about 100 litre per minute, require a 10-minute sample to collect a cubic meter. Longer than that starts to cause potential for elevated desiccation, and that elevated desiccation leads to lower growth promotion test isolates. So because as it lands on a desiccated surface, it's less likely to grow because it doesn't have access to those nutrients. It has access to onto a crusted layer that sits on the surface. Equally so, if I take it in the first couple of seconds and I have a CFU, that desiccation could occur and therefore stress the organism and it doesn't grow. Now, fortunately, we're looking at this 70%. So a recovery rate of greater than 70%, according to Pharmacopoeia, which is it's quite a nice bit of leeway, and it allows for extended sampling. And finally, there's the component of false positive identification, where the sample is drawn either onto a settle plate or through selected holes, fewer holes within that collection profile, then it's difficult to tell whether or not a CFU can be attributed, and here's one right on the rim, whether or not that CFU can be attributed to actual environmental monitoring isolates or buffered, where it hits the surface and circulates and we get small growth, or mishandling. With the BioCap, what we tend to see is this slit lid design also then lends itself to leaving an indentation within the agar below, and providing those isolates sit along the agar path, it's easy to see whether or not they were an environmental, i.e. drawn through the impactor onto the surface of the agar. If we were to have this equivalent microbe or CFU grow out on the edge of our plate, the chances are that singular isolate could be attributed to false counting. So there's a series of, functions when we start to look at the overall impact of a microbial sampler.
So
and with that, I'll turn it over to Julia, who has.
Yeah, thank you, Mark. Let me say that it's always a pleasure to listen you and to learn from your deeply knowledge in microbial and all the different aspects from technical point of view and scientific point of view. So really thanks for your presentation. And I will give to you a short introduction about the solution, because one thing is the theory, one thing is the practical part, so how we can implement what Mark shared with us. And as a particle measuring system, we can provide a complete solution for microbial active microbial air sampling. I will spend just a few slides. If you want to have more details, technical information, specific meeting to speak and to see together one of our solutions. It's just a matter that you contact us. At the end of this webinar, in the last slide, you will see Mark and my contact, as well as you can contact our sales rep in your country, of course. So the solution for active sampling, can you come back to the previous slide? Sorry, Mark. Yes, is there is the portable solution and the remote solution. So we have the Minicat Mobile on left and on the right the Minicat Pro. The names are similar. The application is the same because we are speaking about microbial sampling, but of course one is a portable and the other one is for remote application. Both can be used with BioCapt. As Mark already mentioned in his presentation, we have the traditional stainless steel impactor. Even our traditional stainless steel impactor has this specific drawing. So we have, as Mark presented in the last slide, we have these slits and not the holes. That is a unique, yes, a unique drawing in the market. And we have also the single-use solution of the stainless steel impactor, that is the BioCapt single-use. Let me say that this is not a new solution, because now since 10 years or something more that we produce and sell at a pharmaceutical company. We have really a global customer base for BioCapt single-use, but still remain the innovative solution for a traditional method like the microbial sampling based on agar. So that's still a traditional method. Can you move to the next? Thanks. Minicat Mobile is the portable instrument that we can provide to you. I want to underline 2 points around the Minicat Mobile. Again, we can speak for hours per each product, but for Minicat Mobile, I want to underline that our instrument has this housing and screen antibacterial. So this means that the material we use for the housing and the screen has these antibacterial properties, which help to maintain under control the potential contamination. Let me say in this way. So in addition, the second point that I would like, the second features that I would like to underline is the complete range of accessories. So you can see in this picture, we can really provide a solution for any need that you have. And the one important thing is that you can add the accessory you need anytime you want. So let me say in other words, if today you buy the Minicat Mobile and 1 year from now you need the, I don't know, a remote sampling, you don't need to buy another instrument, but you can just add what you need. We have both the remote connection. We have the isolator sampling. You can recognize, easily recognize the typical drawing of isolator kits. The remote sampling with the BioCapt stainless steel, as Mark explained, also in case you need to collect with a probe. We have even the probe, but Mark well explained that it's better to avoid this kind of sampling because we have the issues around the particle loss. So that's the main point. The compressed gas. This is a very important topic in this moment, thanks to the annex, the last annex released. And for the compressed gas, if you visit our website, there are 2 interested webinars that we delivered before summer. around this topic that cover both scientific and application around the compressed gas monitoring. And of course, we have the BioCap single use. So if you can move to the next slide, the BioCap single use is really the combination of the impactor stainless steel with the agar plate in one single use solution. You can see in the picture. And again, for the BioCap single use, I can really speak for days and not for hours, let me say, but it's a complete, a validated single-use system used for viable, active, viable monitoring sampling. And as it is a single-use solution, you can reduce the costs related to the use of autoclave, the disinfection, and very important, you can avoid out of specification related to the false positive mentioned by Mark in the previous presentation, because the agar is well protected by the device, the top of the device itself. So even the operator that can happen touch the surface, it doesn't touch the agar. So we don't have a false positive. Fortunately or unfortunately, if you have a positive with BioCap single use, this means that there is something your grade A in your filling line. Fortunately, because you already know that is not a false positive, but unfortunately because it's positive. So that's the point. The other important thing, stay around the Annex 1, is that can be used in continuous up to 4 hours. So as Mark mentioned, the value of passive sampling is very, very poor. So that's clear. I think that we all agree on that. With BioCap single use, we have experience that you can depend on the condition, but you can use up to 4 hours in continuous. So with just a few BioCap single use, you can cover the entire process of your production. If we move to the next one, the MiniCut Pro is the instrument, the technology that can be used with the facility monitoring system. So in remote, you have this pump, special pump outside of the grade A, and you can connect to BioCap stainless steel or to the BioCap single use. One of the biggest, let me say this one, the MiniCut Pro is the evolution of the MiniCut Remote, the previous model. And one of the key features that I want to underline is that is a VHP resistant, and we have absolutely complete validation, as well as in compliance with the annex request, so what is included in the annex. So if we want to have a picture, and we move to the next, thanks, a picture of a typical pharmaceutical pharma facility. With our solution, we can support you in any need around monitor and sampling, viable and not viable. You know that particle measuring system started with non-viable. The laser is very famous in the market, but now, as you can see, we can cover every points you need to monitor with active sampling, portable or remote. Same for viable, for non-viable with portable or remote. As well, we can control with the pharma integrity the complete, all the different sensors inside the pharmaceutical, inside your production. Again, this is just an overview, an helicopter view of our solution. If you wanted to discover something more, you can just contact us, and it will be a pleasure to stay in contact with you. I think that now you have the summary, Mark.
I do. Thanks, Julia. Appreciate that for jumping in. So summary, environmental monitoring to determine sterility assurance is a multifaceted exercise. It's no single element is understood to be absolute. So reliance on a single input is inconclusive to demonstrate that overall control. And within critical high risk, grade A environments, we're trying to separate, we're trying to differentiate between zeros and ones, which statistically is very difficult to do. Even USP 1116 has said, well, let's start to look at greater populations to determine what that statistics of small number is. So no single data point can determine the contamination with high confidence. And that's what's led Annex 1 to implement this continuous microbial sampling within the grade A. Taking a snapshot at beginning, middle, and end, or even just at the beginning or at the end, isn't sufficient to demonstrate. We did continuous particle counting, and now they're talking about continuous microbial sampling, such that you can demonstrate with a high degree of assurance, because that's all we're doing. We're just changing the sample volume to be over time reflective of that small piece of area that you're looking at within your filling machine. And those sample points are risk-based. So to extend sample periods, the application of settle plates can be considered, but they're qualitative or at best semi-quantitative, and they're not suitable ideally when differentiating zeros and ones. So to ensure your collection efficiencies are high, you've got ISO 14698, parts 1 and 2, ISO EN 17141, and they help you define what the physical characteristics are of a sampler. And they list out a whole list of elements that should be considered based upon the use, the intended use, and the expected requirements for your application from a sampler. And so they can be used to marry up your current solution versus what environment you're monitoring within. A sample is taken within the process zone close to the critical process, and they're defined as part of your EMRA, your environmental monitoring risk assessment. And there's more of a call for these risk assessments to be performed. Historically, they said, a formal risk assessment, that means documented. Really, they're now driving home the need for documenting your risk assessments. And that's, probability, severity, and detectability. So can you detect with a high degree of confidence whether or not something changes within your critical environments? And the sample should be taken without significantly impacting the airflow patterns and exhaust per Annex 1. And ISO 14698 also mentions that the airflow shouldn't be disrupted as part of the function of the equipment itself. So we've seen it's not just a single element. We have to start to look at it collectively. No, if I have high collection efficiency for 2 minutes, that gives me a high velocity, which yields a higher desiccation, which means I can sample for a shorter time. Now I can either double stack and have 10 minutes, 10 minutes, 10 minutes, 10 minutes, 10 minute sample, and I'm now using a lot of plates, and I'm making an intervention on the line really frequently, so I'll never get production done. So there's a balance between high collection efficiency with high flow rate instruments with lower flow rate instruments, that you lose some of that collection efficiency, certainly physical. Even our own go from whatever it was, 1.2 down to 1.6 with a change from 50 to 25 meters per second. But again, we're averaging out at less than the D50 of 2 micron. And certainly if we use the ISO EN 17141, it's well shorter, it's 0.6 micron. So well within the bounds of what ISO is expecting us to collect. But now we're sampling for a longer period of time. And if we were to do that high collection efficiency, we can only sample for a short period. So it's a balance. And that's why we decided, Julia and I decided to put this presentation together, just so as you can start to see the expanse of different functions that come into looking at an individual instrument. So with that, if you have any questions, then please feel free to get in touch with us or visit our website at pmeasuring.com. And our contact details are there for you to do that. I don't know if we have any questions, Ilaria?
Yep. We received a lot of questions, so I I'm sure we won't be able to answer to everything today. I'll try to give you guys a mix of questions so we can touch on different topics. And we will follow up offline for the others. So first one, is optimal impaction height the same for all microbial sampler and for all media?
Well, no, I think I touched on that a little bit. It's no, it's for us, we have fixed split width. So the only variable for us would be the height of, so that 0.5 to 1.5 millimeters. If you're using a different impactor, then they too will have their own optimum height, and whether or not that's adjustable or not for different media types remains to that manufacturer to determine. So some that I've seen can be a few millimeters, some of them look a little bit odd because they're nearly a centimeter. That does need to be in close proximity, otherwise you're going to lose that efficiency. So it depends, but data should be available as to what the width to height to S1 versus S2 looks like for any impactor. And if your supply doesn't have that, please feel free to ask us, and I can put it into my calculator. I can work it out for you.
Good, thank you. Next question. Is your portable in compliance with ISO 17141?
Yeah, I can take this one. Yes, Minical Mobile is in compliance with both ISO, so the new one 17141 and the previous one still valid because correct mark is still in place, the 14698. And yes, we can provide the evidence of this compliance and validation.
Perfect, thank you. Next one, is isokinetic sampling important within isolators, and what tolerances are there?
Oh, I'm guessing that's me then. Isokinetic sampling is important if you don't want to disrupt airflow. And there's a difference between disrupting airflow and disrupting laminar flow. So an isokinetic probe won't disrupt laminar flow. But as soon as you put anything flat in, as opposed to the knife edges that we saw with the isokinetic probes, as soon as anything flat goes in, you're going to create turbulence. The flat plane, most impactors are kind of hockey puck shaped, and you'll get turbulence occurring on the back face of them. You'll end up with a negative hole pocket as the airflow pulls past, and that'll suck air into it and create turbulence. So it's not critical. And in fact, quite the reverse happens. The wider the collector, if you're below the first air plane, you will create turbulence, but you're also collecting at a greater diameter, which those large particles are going to maintain their momentum and be collected regardless. We're still going to collect. So laminar isokinetic sampling is critical for laminar flow, so you're not disrupting laminar flow. But in unidirectional airflow, and certainly first air, it's not a critical function. The critical function is that you don't create turbulence above critical high-risk activities, causing a disruption to first air. And it's that disruption to first air that Annex 1 looked at and went, and that was why they selected the language that they did.
And let me add that if you are interested in isolators, we have a brand new webinar just recorded last month, which Mark was a speaker for that as well. So feel free to check it out on our website. And I'd like to move on to the last question for today. And Julia, this is for you. Can the BioCap single use be used only with your equipment or not?
I will answer with a smart answer. I always say that if you use our vacuum source, it's better. But the truth is that the BioCap single use can work with any pump, at least any pump with a controlled vacuum. What is important is the flow rate of this equipment that must be for the standard one between 25 and 50. So again, the answer is it works with any source of vacuum if you can connect, of course. I'm referring more to the remote connection. With the portable is more complicated. So it works with Minican Mobile for sure, not with the other portables, but with the remote connection, if the flow rate is correct, yes, it works.
Yeah,
even ours is better.
Yeah. I'll add to that because I've used one with a particle counter running at 28.3 liters per minute. Now the particle count data is a little bit odd, but it's so long as it's a controlled vacuum source, to your point, Julia, it's fine.
Yeah, exactly. Good. This is the point.
Thank you both. And that concludes our time for today. And I would like everyone for attending. If we were unable to address your question, and I know that we weren't able to address a lot of them, our presenter will follow up directly. And let me remind you again that you have the slides and the certificate of attendance in the resource section of the platform. We hope that you'll take a minute to reply to our survey that will pop out on your screen at the end of this webinar. And again, let me invite you to visit our resource center on pmeasuring.com for more webinars, white paper, articles, and yeah, feel free to get in touch with us for more information on our products and solutions.
Thank you for your time. Yeah. Thank you,
everyone.
Bye. Bye.